Alright, so this is the tutorial on drawing cyclohexanes, and so if you look at cyclohexane as we would just draw it on paper, it seems that it looks like it's flat, right? But really, it's not. It's going to adopt conformations that lower strain on it. So what we do is we look at it as a chair conformation. And so the easiest way to do this is to essentially draw two parallel lines and then connect the dots in the middle. So now you draw the two there and then connect the dots, and we can see that we have now what we call a chair conformation. Now we need to look at some of the bonds that are on there. We often call these bonds axial and equatorial bonds. So this chair conformation has both axial and equatorial bonds. So let's look at axial first. So I'm going to start here at the top, and I'm going to put one up, and then go down, then up, then down, then up, and then I'm going to go down again there. And what you can see is that all of these are now what we refer to as axial bonds. Now let's fill in the equatorial bonds. So equatorial bonds are going to we'll start at the same carbon, and now we're going to go kind of a down at a slant, and up and down and up and down. Oh, let me fix that there. All of these are now what we refer to as equatorial bonds. I left off the last one just to make it less cluttered. Now let's put all of these together. Let's draw all of the bonds that we would have. Let's draw them together. Now, just as a side note, remember that if you're drawing this, if you draw a line like so, and you don't label a hydrogen there or something, that indicates a methyl group. I'm just putting in the lines just so you can see where the bonds should be. So here we have all of our axial bonds. And now we're going to fill in our equatorial bonds. And now we have all of the bonds together. So let's have a conversation regarding stability. The idea is that we want all of our largest groups in the equatorial position. And I'll explain why momentarily. So here we have an axial methyl group, and then we can undergo what's called a ring flip. And if I draw the ring flipped version, you can see that now the axial methyl becomes equatorial. And the fact that the methyl is equatorial means that this is more stable. But wait a minute. ring flip. What is that? Well, if we look at a cyclohexane in the chair conformation, and we see that we have this methyl group here in the axial position, what we can do is we can actually, if I make a note here and point out the carbon that the methyl is on, we're actually going to take that methyl group and we're going to, where that carbon is, we're going to pull it down. And so if we do that, it causes the carbon on the opposite end to go up. And so this is what we refer to as a ring flip. So what was axial becomes equatorial. So you can see there that we're going to pull that methyl group down. Then I'm going to reverse the slant on my ring here, and now that methyl group is equatorial. So you can see this is the same carbon. So we're not moving carbons. We just change the position. So the methyl group is still on the same exact carbon that we had, we just changed the position there. Again, the other end of this carbon here on the other end is going to go up. So it's kind of like if you pull down on one side, you're going to push up on the other side. So now in this example, the conformer to the right, which has the methyl group in the equatorial position, that one is the one that's more stable. So our equilibrium will lie to the right. So why is it that this axial is unfavorable? And what do we talk about when we refer to cis and trans? Well, let's look at this. So here I have a methyl group, and now I'm going to put another methyl group in the axial position. Notice that both groups are axial. And in this case, both groups, I have one group that points up and one group that points down. So that means that we have one up and down, so that's trans. They're on opposite faces of our ring. So if I were to draw it again, whereas I put these guys where I have one axial and then put one equatorial, now I have two CH3 groups. They're both pointed up on the top face of our ring. And so therefore this would now be cis. So the idea is if you have something that is 1-2 substituted, you then have one that is cis, or one that is axial and one that is equatorial. That gives you the cis conformation. We refer to this as 1-2 cis. Again, starting from this carbon here on the right, and now let's move to the carbon number 3. So now what I have is I have two groups. They're both axial, and they're both pointed up. So 1-3 here with two axial groups is cis. They're both pointed on the top face of our ring. Let's look at another example. CH3 again here at the top on number 1, and then I'm going to move now, instead of axial, I'm going to put the other CH3 in the equatorial position. So now I have one group that is equatorial and I have one group that is axial. So you can see clearly one group is up and one group is pointed down now. So this gives us the trans relationship. One up, one down, that's trans. Alright, so let's move over to carbon number 4 now, and now you're going to see I have both now are axial bonds, both CH3s, and one is up, one is down. So two axials in the 1,4 position. Count, I'm 4 carbons away. This gives me a trans relationship. Now, if I draw another ring here and I put one axial, one equatorial, that gives me 2 of them that are on the top face of the ring. And so therefore I have one axial, one equatorial, and in the 1,4 position, they are indeed cis now. So I hinted about this earlier, and I mentioned this stability issue. Why is axial so unpreferred or unstable in that matter? Well, what it has to deal with are what we call 1,3 diaxial interactions. So if I draw a ring in the chair conformation here, I'm going to put a CH3 here, and I'm going to draw this CH2, and I'm going to stick the other hydrogen out. And then I'm going to put a hydrogen there in the axial position and another one there in the axial position. And now what you see is that from that methyl group, every 3 hydrogens away, I have an interaction. These guys are bumping into each other, right? So you can see on each case, they're 3 carbons away. The hydrogens are sticking out there, and they're bumping into each other. This is what we refer to as 1,3 diaxial interactions. I have 2 of them, and they go out 3 carbons in each case. These cause high amounts of energy and strain in our structure. So therefore it's more favorable if we put the methyl group in the equatorial position. We don't have these 1,3 diaxial interactions. So now let's look at an example. Let's draw let's draw cis one 4 dimethyl cyclohexane. Alright, so if I draw this, I'm just going to start. You can just arbitrarily pick how you want to draw it. And so I'll just put these guys together, and I'll just start with a CH3 in the axial position. Now I need to make this cis, so I'm going to count 4 carbons away here, and I need to put another carbon that goes up. So I can't have it axial, it needs to be equatorial. Therefore I can get the cis conformation. And what you can see is I have one group that is axial, and I have one group that is equatorial. Now if I undergo a ring flip, you can still see that by moving the methyl group, the carbon there, down, that converts it to equatorial, and then I have the other guy that was equatorial now is axial. I still have one equatorial and one that is axial. So in either conformation, these are both equal in energy because I still have one axial, one equatorial, no matter what you do. And this will be what we refer to as cis because they're both on the top face of the ring. So they're both going to be equal in energy. Now, if I squeeze in down here at the bottom, and let's say we're going to draw, just as another example, let's do cis 1,3 dimethyl cyclohexane. Now, if you can squint and see that name, I'm going to draw these two lines here, and then I'm going to start arbitrarily again. I'm going to put this CH3 in the axial position at that carbon. Then I'm going to come over here to carbon 3, and now I know that I have to make it cis, so axial again has to go up here at this point. So I'm going to put my CH3 up in the axial position. Then if I undergo a ring flip, what happens is what was axial becomes equatorial. And then now you can see the difference. Both groups are cis, but now this guy is more stable because I have the larger groups, both of them are in the equatorial position. And so this lends more stability because I don't have those 1,3 diaxial interactions in this case. So the equilibrium lies to the right.